Welcome back for our next discussion in 8.3, where we're looking at evaluating different types of trigonometric integrals. In this discussion, we're going to look at a different scenario. If you remember in the last video, we talked about, well, what if one of the powers was odd and positive? In that case, it falls into a U substitution technique. We isolate one of those odd powers, save it for our du or differential piece for the U sub. We'll convert the remaining even powers in terms of our Pythagorean identity. That's where the identity comes in. And then at that point, we use a U sub. Well, that doesn't cover all scenarios. And by all means, this section doesn't cover every single possible scenario. We may encounter some random trig integrals that we're going to need to think about and discuss in the future sections. But this gives us an idea of some other types of scenarios that if we run into them, we can address. And so if one of the powers is odd and positive, we can address that scenario with sine and cosine. We'll look right now at, well, what if both of them are even? This doesn't cover all scenarios, but both of them are even. When I have powers of sine and cosine, what do I do then? And in that case, we're going to actually use a different type of identity, use half-angle identities from trigonometry. And then we'll also explore, well, what about secant and tangent as well? And in the next section, it will make sense, well, why are we only talking about sine, cosine, secant, and tangent? What about the other trig functions like cosecant, cotangent? We can discuss those, but in terms of trigonometric substitution, we're only going to be looking at certain trig functions and therefore certain types of trigonometric integrals right now. And so let's look at sine and cosine again, but in the scenario that, well, what if both powers are even? In this case, we're actually not even going to use a U substitution technique. We're not going to use a technique of integration. Here, we will just do direct substitution. Direct substitution with a trig identity. So not an integration substitution, but just a direct substitution with a trig identity. In this case, our half-angle identities. So not our Pythagorean identities. If both powers are even, we will be using one of these two identities. If it's an even power of sine or an even power of cosine. And so how will just a direct substitution allow me to integrate? Let's look at an example. And let's look simply at sine squared theta d theta. If I'm integrating sine squared theta d theta, I am not going to use my Pythagorean identity to write as 1 minus cosine squared because that doesn't help me. Now I have an even power of cosine. So in no way do I get the answer by converting it using a Pythagorean identity, like we did in the last discussion. I can't pull one aside and convert the rest since they're even. Right? Pulling one aside, yes, I have something, say, for a differential, for a substitution, but now the remaining powers are odd. And I don't have identities for odd powers of trig functions, only even ones. So since I'm starting out with an even power, it kind of leaves me not being able to work with it too much, aside from just a direct substitution. Since the Pythagorean identities will just replace an even power with another even power, that's not going to be useful. And that's where the half-angle identities come in, because it takes an even power, sine squared or cosine squared, and replaces it by an odd power, a single power of cosine. Notice that both half-angle identities are cosine regardless of sine or cosine. The only difference is whether it's a plus or minus sign. The over 2 shouldn't scare us because when it comes to integration, that's just a constant in the denominator which can be pulled out of integration. Even the 2 theta here inside of cosine shouldn't scare us. We could, if we want to do a U sub, or if we're comfortable with U sub and the chain rule, we should be able to integrate that directly. And that's exactly what we're going to do here in this first example. Since both powers are even, we have, well, no cosine, and the only power we have here is 2 of sine. I'm going to use this half-angle identity directly. I'm just going to rewrite this integral as 1 minus cosine of 2 theta over 2. Like I said, that 1/2 in the bottom doesn't scare me. I'll factor it out of the integral, leaving me with this. And at this point, we can actually integrate it directly, depending on how comfortable you are with the chain rule and U sub. The first one is fine, and the antiderivative of 1 is theta. Remember, not x, right? We're dealing with theta in this discussion. Minus the antiderivative of cosine. Remember, this is just a single power of cosine. The antiderivative of cosine is sine. So we get sine of 2 theta. Well, since it's not just cosine of theta, but rather cosine of 2 theta, we do have to be a little bit careful of the chain rule. and technically a u substitution because I can replace 2 theta by u. The derivative of 2 theta is just 2, meaning I just need to adjust the constant, and what that will end up giving me is a 1/2 then, or a 2 in the denominator. This is what will always happen then. And then plus c, and we're actually done. No substitution was needed. We were able to integrate this directly just by using a trig identity. We can distribute the 1/2 if we want. All right, well that's great. Well, what if we have multiple even powers? Let's look at what happens if we have sine squared, cosine squared. Let's throw both of them in and make both of them even. So let's box this out real quick so we don't run into it. Start here, and let's do sine squared theta, cosine squared theta. Both of them are even now. So I don't employ the technique that I used in the last discussion where we had an odd power, we pulled one out. In this case, both are even, so I'm just going to do direct substitution with the trig identity with my half angle ones. And so, just a direct substitution, sine squared, 1 minus cosine of 2 theta over 2. Cosine squared, 1 plus cosine of 2 theta over 2. D theta. Again, those 2's in the denominator don't scare me, so I can factor out both of them. So pulling a 2 out here and a 2 out here gives me a 1/4 out front now. 1/2 times 1/2. And then what we end up having is, looks like a binomial. Binomials multiply together, and actually they're conjugates of each other, which is great when you go to FOIL this out. Since they're conjugates, that means the outside and inside terms will cancel when you FOIL. And if you FOIL this out correctly, you get 1 for the first terms. The outside and inside terms are opposite. That's being conjugates gives me that. So they cancel. And then don't forget we need to multiply the last terms. That gives me a minus sign. And actually now gives me cosine squared of 2 theta. So we get cosine squared. Now if we get cosine squared, we may think, okay, we're almost done. We should be able to integrate this directly. Well, not necessarily. In this case, I do know the antiderivative of 1. That's great. But if you look at that second term, it is no longer cosine of 2 theta, but now cosine squared of 2 theta. Well, what does that mean? That means I have an even power of cosine. I only have 1 power or 1 cosine here, no sines or anything like that. And the only power I have is even. So again, that means I need to use these identities one more time. And so if I integrate this, I mean, I could do the first part, 1/4. And then antiderivative of 1 is theta. That part I can take the antiderivative of minus the antiderivative of cosine squared theta. Well, again, even power. So I can't integrate it directly. I can't use my u sub using my odd power. So again, I will use a half angle identity. And we just need to be careful. Cosine squared becomes 1 plus cosine of 4 theta over 2. Again, where does the 4 theta come from? Comes from the fact that I'm using a half angle identity. And the identity says whenever time you use it, you take whatever that angle is and you multiply it by 2. Here, we went from theta to 2 theta because, well, we followed the rule. Theta gets multiplied by 2 and gives me 2 theta. Here, we started with 2 theta, meaning if I use this identity again, I need to multiply 2 theta by 2, giving me now 4 theta. So I can still use this identity, but every time I use it, I need to double whatever theta is. And the first time I use it, well, it's theta to 2 theta. The next time I use it, it's 2 theta to 4 theta. If I had to, for some reason, use it again, which we won't have to, but if I had to, it would become 4 theta to 8 theta, 8 theta to 16 theta, and so on. Now, again, we can distribute the 1/4 if we want. I can pull the 1/2 out, giving me a 1/8 out front. And now we're at a place where we can integrate this directly. We have a 1, which we can take the antiderivative of, and cosine to the 1, just cosine by itself, which we can take its antiderivative, giving me a final answer of 1/4 theta minus 1/8, and then theta here, plus, well, antiderivative of cosine, right, would be sine of 4 theta over 4. Again, because of the chain rule, and if you want to do a simple u sub, you can, but if you're comfortable with u sub, you can go straight from here to here. Distributing my negative 1/8, which we should not forget to do, we get 1/4 theta minus 1/8 theta, which we can combine if we want. And then minus, well, 1/32 sine of 4 theta. Plus. And so we get this for our answer. And so again, we solved it. We never used a U substitution or integration technique. All we did was use these identities. In this case, we had to use it 2 times over. We used it for both of these. We FOILed it out. We got to here. We realized, oh, I need to use it again on this even power. Rewriting it here gives me now, again, this, which now we can integrate directly. We would, of course, mimic this again and again. If it was like sine to the 4th, we would do the same thing. So I'll get us started. Just to kind of write it out. Say we had, well, let's actually do cosine to the 4th. Say we had cosine to the 4th. So an even power, no signs this time is cosine to the 4th. Remember, just like in the U sub technique, remember cosine to the 4th is cosine squared squared. So that means I have a square of that identity. The identity for cosine squared is here. So we can rewrite cosine squared as 1 plus cosine of 2 theta over 2, but then that would need to get quantity squared. Now don't worry, right, when we square, we can square the numerator and denominator separately. Squaring the denominator gives me a 1/4, which can be pulled out of the integral anyway. And then we would need to square this term here. Which again, just like we did in this example, we just need to FOIL some stuff out. In this case, we're squaring a binomial instead of multiplying conjugates. And so just being careful, we're going to get antiderivative of 1 plus 2 cosine of 2 theta plus cosine squared of 2 theta. D theta. At this point, now it falls kind of back into this scenario here. We can take the antiderivative of the first term, which is theta. We can actually take the antiderivative of the second term, right? Plus antiderivative of cosine is sine of 2 theta over 2. Sine of 2 theta over 2, that means the 2's would cancel, so I'm just going to get sine of 2 theta. Plus, well, we actually can't integrate the last one, but we would just have to use our half-angle identity again on this one. So we can integrate the first 2 parts of this definite integral, because integrals break up over sums. The last part, though, we can't integrate it directly. We would just have to use this angle identity again, just like we did here. We actually did this directly, right? Cosine squared of 2 theta now becomes 1 plus cosine of 4 theta over 2. And we would dot, dot, dot complete it in the same way we did the last example, giving us our answer. So when we have even powers and only even powers, right, that's important, both even powers, we're not going to employ or use a technique of integration like U sub or anything like that. Instead, we are just using a identity. Direct substitution with a trig identity. What identity, though, is important? We're not using the Pythagorean identities in this case. We are only going to be using the half-angle identities. And so we'll pause here, and we're going to look for a brief moment. We're going to look at what happens when we integrate with secants and tangents. And so we'll move the board a little bit over and look just for a second at, well, what if we have secants and tangents? And so we still have our trig identities here, which actually are going to be useful again to me. We're going to go back to our trig identities using our Pythagorean one. And what about in general, we have powers of secant and tangent. Secant to the n and tangent to the m instead of sine and cosine. And all I'm going to do is remind us in this scenario, we're not going to write down some half-angle identities, or try to use U sub. I'm going to remind us that we know the derivatives of tangent and secant. The derivative of tangent is secant squared. The derivative of secant is secant tangent. Meaning, if you want to do a U sub, as long as you have a secant squared multiplied into the integral, you can replace tangent by u. And if you want to do a U sub, as long as you have a secant tangent multiplied into your integral, that will be your du, then you can replace u by secant. U is your replacement, then you need its derivative replacement as well. So you want to replace u by secant or tangent, then you need to make sure that there's a secant squared multiplied in. You're going to replace tangent by u. And you would need to make sure there's a secant tangent multiplied in if you're going to replace u or secant theta by u. And so that's what we're going to implement again in this case. We're going to go back to the first technique, the u sub technique in these scenarios. And so what we're going to do is we're going to, in this case, secant cubed times tangent, I'm going to realize that, hey, wait a minute. If I pull one of the secants away, then I can have a secant tangent isolated, and then the remaining powers of secant I can replace using a u sub. And so just like the u sub technique we learned before, I'm going to take away one of those powers of secant. I'm going to isolate it. Why do I do that? Because I have a tangent here, and if I pull one secant away with it, now I have the derivative of secant multiplied into this integral. That's great, as long as, well, we replace the rest, and well, we have only left secants multiplied in. And so if I want to replace secant by u, we can do that now, because we have its derivative multiplied in. So we just want to keep an eye out for that. Just like sine and cosine, we need to be comfortable with the derivatives of tangent and secant as well. Doing this u sub actually leads to a very nice integral. Secant squared now becomes u squared. This whole part now just becomes my differential to u. And we can use our power rule and be on our merry way. U is secant. And we're done. Same thing here. In fact, we see it directly. Look, we have secant squared multiplied into this integral, which is the derivative of tangent. So if I just let u be tangent of theta, that secant squared theta d theta now becomes my differential, and we get, again, a nice u substitution. In this case, we didn't even need to pull anything away, right? We get u cubed times du. So tangent becomes u, so u cubed. Secant squared d theta is now my du. And that's because I'm comfortable with the derivatives of tangent and secant. And so now doing the power rule, we get our answer. Again, we're here. Now, I'm doing these on purpose. We're not trying to pretend that secant and tangent integrals are easier than sine and cosine. We're just understanding the idea that, well, the techniques that we introduced, or not introduced, the identities and things that we introduced with sines and cosines kind of transfer over to secants and tangents as well. We just have to be a little more careful, right? The derivative of tangent is not secant, it's secant squared. Derivative of secant is not tangent, it's secant tangent. Right? And so if I want to use kind of that u sub technique that we talked about with sine and cosine, well, I need to pull out the appropriate thing. And either I need to have a secant tangent isolated and then replace my secants by u, or I need to have a secant squared isolated and replace my tangents by u. Now, in this case, this illustrates, well, kind of the one-off thing, right? We're not talking in this section about all types of scenarios we can run into. I can write all different scenarios with trig functions all day, and it's not that every single trig function that we need to integrate falls into one of these scenarios. We're just introducing different kind of ways to tackle certain types of trig functions in terms of integration. And so in this case, right, tangent squared, well, I don't have any secants at all, and so there's not really a u sub thing here. I don't know directly the antiderivative of tangent squared. If it was a secant squared, then we'd be in good shape. And the antiderivative of secant squared is tangent. And then I remember, well, this Pythagorean identity. I remember the fact that tangent squared can be written in terms of secant squared. And so if I actually just use an identity here and replace tangent squared as secant squared theta minus 1, that's actually beneficial to me because I know the antiderivative of secant squared. That's tangent. And so now I can actually answer this directly without any sort of u sub or any special technique, just by using an identity. Antiderivative of secant squared is tangent. Antiderivative of 1 is theta. So you may be able to answer directly. You may use one of these identities. You may be able to use a u sub, remembering the derivatives of tangent and secant. But all this to say is It's not a comprehensive section. It's not going through all the different scenarios with trig. It's just giving us some more tools. It's kind of preparing us for what's going to come in the next discussion, which is trig substitution, where we're going to take algebraic functions and replace them with trig functions. And when we do that, we need to be a little bit more comfortable and remind ourselves of our ability to be able to solve trigonometric intervals. And so this section is just kind of a way to talk about, remind ourselves, and kind of evaluate different scenarios that you might run into. Again, it's not comprehensive. It doesn't answer all types of scenarios, but it gets us a good start and gets us thinking about how to answer trig intervals, either with U substitution, a technique we already know, using some identities that we learned from trigonometry, some things that we want to keep in the back of our minds as we move forward. And so we'll cut this section here, and when we come back, we'll take all of this knowledge and apply it to being able to use what we call trigonometric substitution. That will be the next video.